Welcome back. The objectives of this video are to define the determinant, and we'll do a sample with that to find the determinant of a 2x2 matrix. We'll also explore determinants of square matrices, so 3x3 and larger. We'll calculate the minors and cofactors, which we will need in order to define the determinant. And we will do an exercise called expanding the cofactors, or finding the determinant of a 3x3 or larger matrix. So objective 1, the definition of a determinant. The determinant of a matrix is simply finding the difference of the products of the two diagonals of the matrix. What we will do here is we will take A1 times B2 and subtract A2 times B1. So the determinant is the difference of the products of the two diagonals of the matrix. Be careful, order matters, so make sure you start in the upper left and go to the lower right, and then go to the lower left and to the upper right. Don't reverse that process. We will also use essentially the absolute value bars here, but it's not absolute value, to represent the determinant of a matrix. So we'll use this notation, the determinant of A, or the vertical bars surrounding the A, to indicate we're looking for the determinant of that particular matrix. So here's an example of calculating the determinant of a 2x2 matrix. It is simply 2 times 2 minus 1 times a minus 3. So 4 plus 3 is 7, and we have calculated the determinant of that matrix. Now, not all matrices are 2x2s, and in order to calculate the determinant of a larger matrix, 3x3 or larger, we'll need something called the minors and the cofactors in order to do that. So we've got a fairly confusing definition here of minors and cofactors, but if some matrix A is a square matrix, then the minor ij, which is essentially a location in the matrix of entry ai sub j, is the determinant of the matrix, obtained by deleting the ith row and the jth column of A. The cofactor ci sub j of the entry ai sub j is given by -1 raised to the I plus j times mi sub j. And we'll see this later on, and I'll explain this in another video, exactly what this looks like. We'll also provide a sign pattern for cofactors. It says here they're at the right, but I have them below. And it says notice the odd positions where I plus ij is odd, have negative signs, and even positions where I plus j is even, have positive signs. So that's going to be important. But what's going to be most practical is doing a sample. Once you do these a few times, you get the hang of it. Finding the minors and cofactors of a matrix. So we have our matrix A here, and we'll want to find all the minors and the cofactors. Process, and we talked about this a little earlier in the definition when it says to obtain by deleting the ith row and the j column. That is exactly what we're going to do here. To find the minor M11, meaning the minor of the first row and the first column, delete the first row and the first column of A and evaluate the determinant of the resulting matrix. M11, we delete those rows and columns. We have a leftover matrix, a 2x2 matrix. So we multiply -1 times 1 minus 0 times -2, and we get -1. So that is M11. So that's our first minor for that particular location. And now we have to calculate all the minors for this particular matrix. So we repeat the process. M12, first row, second column, we delete those. Our resulting 2x2 matrix has diagonals 3 and 1 and 4 and 2. So 3 times 1 minus 4 times 2 equals -5. So that is M12. So I've calculated the minor for that location. So then I'll quickly go through the rest of the minors for this particular matrix A. M13, delete the first row, third column. My resulting matrix, 3 times 0 minus 4 times -1. So M13 is equal to 4. And then I moved on to the second row. I deleted the second row in the first column. My resulting matrix left over, 2 times 1 minus 0 times 1. I get 2. And then M22. You can see I've deleted that row and column. My resulting matrix, 0 times 1 minus 4 times 1 is -4, and so forth for M23. And I repeated the process again for the third row, repeating the first row, the third row, and the first column, calculating my determinant, third row, second column, delete that, calculate my determinant, third row, third column, my resulting 2 by 2 matrix, and my determinant, and calculate that. So now I've got all my minors. I've got them listed below here. And notice I put them in the same order as my matrix. So they're in the particular location in our grid here. So now that we have the minors, we need to calculate the cofactors. In order to calculate the cofactors, we need to get a handle on this grid. So this was that business early on in the definition with the cofactors of the entry ai sub j is given by this particular formula, -1 time raised to the I plus j. Specifically, the sign patterns, the odd positions have negative signs and even positions have positive signs. I found it pretty easy just to memorize the pattern. C11 was positive, and then the signs change. Positive, negative, positive. And then I go below in row 2, negative, positive, negative. And that pattern really holds for the 3 by 3 matrix, the 4 by 4 matrix, and so on. We start with positive, and then we just alternate our signs as we move across the row. In the second row, we start with negative, and we alternate the signs as we move across the row. Go back to positive for the third row and alternate the signs, and that pattern just continues over and over again. So now that I have all the minors listed here again a second time, and I have my sign pattern listed above here, I can apply my sign pattern, my 3 by 3 for my 3 by 3 matrix, to my minors to gain my cofactors. So M11 is positive. So a positive -1 is still -1. So my cofactor C11 is -1. M12, the sign is negative, so the opposite of a -5 is a +5. So my cofactor for row 1, column 2 is 5. And again, we follow the patterns. Positive of a +4 is 4. Now row 2, we're going to go negative, positive, negative. So the opposite of 2 is -2. Positive of -4 is -4. The opposite of -8 is 8. Then I grab my signs for the third row and I bring them down and I apply it to M31. So that's going to be positive, negative, positive. So the positive of +5 is still 5. The opposite of -3 is 3. And the positive of -6 is still -6. So again, we've written the minors and cofactors in matrix order. Now that we have the minors and the cofactors, we can calculate the determinant by expanding the cofactors. Okay? And that's really what it's called. Expanding the cofactors or calculating the determinant is essentially the same thing. And we can do that for a 2 by 2 or greater matrix. And we will see this for the 2 by 2 is pretty straightforward. So we'll use this for 3 by 3 and larger. So let's calculate the determinant of a 3 by 3 matrix. Well, here in our definition, to find the determinant, we simply take A11, well, that's is simply our uppermost left row and column, and we multiply it by its corresponding cofactor. we add it to A12 and multiply it by its corresponding cofactor, and we do that until we complete the entire row. And once you have that sum for that particular row, you have calculated the determinant. So what does that look like? Let's find the determinant of a 3 by 3 matrix, or if you will, you might see in the instructions, let's expand the cofactors by cofactors of a 3 by 3 matrix. So if we want to find the determinant of this matrix, we'll need all the minors and the cofactors. Good news is we've already done that. We did that in the previous sample. So we're going to use the same matrix from the previous sample. I'm going to carry down our cofactors from earlier in the problem. So we have our cofactors here of the matrix. So now all we have to do is choose one of the rows, multiply each term by the corresponding cofactor in that row. We have chosen to use the entries in the first row. So we're going to grab our cofactors from the first row, and we're going to multiply them by our entries of our matrix from the first row, and we calculate the determinant. A for row 1, column 1 was 0. Our cofactor was -1. A for row 1, column 2 was 2, so we multiply it by its corresponding cofactor of 5. And A for row 1, column 3 was 1. We multiply it by its cofactor of 4. We add all that together, and we get 14. That would be a first row expansion. If we did a fourth row expansion, then I would grab my cofactors from the fourth row, and I would bring them down, and I would multiply them by the entries from our matrix of the fourth row, or pardon me, of the fourth row. Why do I have 4 rows? I guess that would be a third row expansion. A 3 by 3 matrix is only going to have 3 rows. I beg your pardon. So a third row expansion, 4 times 5 plus 0 times 3 plus 1 times -6 still is 14. So it doesn't matter which row we use as long as it's one of the rows in the matrix, and we should get the same determinant. So that wraps up finding the determinant of a matrix, and we'll get some more practice with that when I see you in class.